Alright, so if I have carbon 12 and carbon 14, they're isotopes because they have the same number of protons, right? They each have how many protons? 6, right? Carbon 6, so they each have 6 protons. But carbon 12 has 6 neutrons, whereas carbon 14 has 8 neutrons. And so they're isotopes because they have the same number of protons but different number of neutrons.
The atomic weight is like the average?
So the atomic weight then, yes, is the average mass of all known isotopes. So the fact that the atomic weight of nitrogen is 14.0067 tells you that most of the nitrogen in the world has 7 neutrons. It's nitrogen 14. But then sprinkled here and there we might have a 15, and that's going to raise the average just slightly. Alright? So that's why the atomic weight is not a whole number. It's not the mass of the neutrons. I mean the electrons. Alright, so, and when I write for this particular nitrogen, let's say this is a nitrogen 14, what does that 14 represent?
Neutrons.
Good, that's called the mass number, and it's the protons plus the neutrons. And then if there is one, we write the charge in the top right hand corner. So for example, let's say you've got let's do fluorine 18 with a -1 charge. Tell me, please, how many protons, how many neutrons, and how many electrons? Yeah. Okay. Yeah, we always start with protons because we know it's fluorine, so we know for sure that it has 9 protons by definition. Fluorine has 9 protons.
9 neutrons.
Okay, so it must have 9 neutrons because the total of protons and neutrons is 18.
And it has 7 electrons.
And it has how many electrons?
7. How about 10?
10.
Where'd you get? I don't know.
Where'd you get from?
If it has a -1 charge, that means it has how many more negatives than it has positives?
1.
Just 1. And so if it has 1 more negative than it has positives, how many positives does it have? 9. So it must have 10 electrons. Incidentally, speaking of that, what's the charge on an electron? Negative 1.6 times 10 to the -19 coulombs. Now, you don't have to know that number, but just know that it's a really tiny number because a coulomb is really big. But here's what I do want you to know.
Why would you measure it in coulombs so big and the charge is so small?
Why not?
Good question.
That was a good question.
That's a very good question.
It's recorded.
I don't know.
Oh, you are recording?
Yeah, -19 power.
It was a good question.
Very good question. I don't know. I'll have to check.
That's why I measure so small.
Yeah, it's got to be tied in at the end, but I don't know. But it's a fundamental. The charge is fundamental, so I don't know. That's a good question. All right. What's the charge of a proton? Positive 1.6 times 10 to the -19 coulombs. So they're the exact same magnitude of charge, opposite sign. That's not terribly surprising, right? Because a proton cancels out the charge of an electron. But the more you think about it, the more interesting that is. Because what do you know about the masses of protons and electrons? Yeah, protons are like 1,000 times more massive than electrons. And yet, they have the same magnitude of charge. That's interesting. It's imperative, right, for the stability of the atom, and yet it's pretty cool. So, even despite their huge difference in mass, they have the same charge. All right. Let me give you a few to practice on. What about, let's do, if I had sodium 23 with a positive 1 charge. Okay, you start with protons. There's 11 protons because by definition sodium has 11 protons. Good, so therefore it has to have 12 neutrons because the mass number is 23, so protons plus neutrons is 23, so that means if 11 of them are protons, the remaining 12 have to be neutrons. And then what?
10 again.
Then 10 electrons because it's got one more positive thing than it does negative things. It has 11 positive things, so it must have one less negative, so it has 10 electrons. Alright? What about... And by the way, when I'm doing these, I might make up an isotope that doesn't even exist, but that's okay because it's just for practice. But let's say there's this one. Okay. What was it? Oh, sorry, this should have been, let's make it 68. There we go. Good. It's 27 because there's more positive things, and so this has to be 2 larger than that. Alright? And we're not going to discuss why now because we're going to come back and pick it up when we do atomic and nuclear later. But I want you to note something. What's happening to the number of protons and neutrons as we move up the table? We're getting farther apart. And like I said, we'll explain why when we come back to that, but I just wanted to point out to you. The higher up the table you go, the more neutrons you have compared to the number of protons. Alright, questions on that? That should have all been all review. So, okay, good. So now let's go back to this thing where we have some positive charge. And we'll call that positive charge A. And we're going to put it next to another positive charge, which we will call B. Now, what do you know that's happening with A and B? They're repelling. So there is a force on A in which direction? Good, to the left. So there's this force that's B acting on A, right? And then there's a force on B. Good, that's in the opposite direction. It's away, it's to the right. And that's the force of A acting on B. Well, let me ask you this. What is true about the relationship of the force of A on B and the force of B on A? Is it equal? Well, we'll start with this. What if the magnitude of the charge on A is equal to the magnitude of the charge on B? Then they're equal, you think? What if the magnitude of the charge on A is larger than the magnitude of the charge on B?
A acting on B is going to be greater than B acting on A.
Always equal. Why? what is that charge, or that force, equal to? If we wanted to know, what information would we need to be able to determine the magnitude of that force? Dang it, if only I'd taken notes last time.
Oh, it's like Newton's law of universal gravity. No, it's Coulomb.
Okay. Coulomb's law,
Coulomb.
which says I need, good, the constant K.
Equals K, charge or charge 1, charge 2 over radius.
Good, I need the charge of one and the charge of the other, and the distance between them, right? Well, which one is that for? Is that for the force of A on B or the force of B on A? It's the same. Because what we have here is a what? An example of which law that you were just reminded of on your benchmark?
Equal and opposite.
Okay. Third. Yeah, Newton's third law. Equal and opposite reaction. It's action-reaction pairs, right? The force of A on B is equal and opposite to the force of B on A. And they both equal K Q1 Q2 over R squared. And so even if Q1 is much larger than Q2, both Q1 and Q2 figure into the equation to determine how strong the force is. And because they're an action-reaction pair, they're going to be equal and opposite on each other. Now, last time we talked about the connection between Coulomb's law and Newton's law of universal gravitation. And so let's just belabor the point just a little bit more. Here's an example of, there's Earth, and there's me. Yes, I'm very large. I don't go flying off of Earth because of gravity. There's a gravitational force on me of the Earth acting on me. How does that compare to the gravitational force that I exert on the Earth? The same? You mean I'm pulling on Earth just as hard as Earth's pulling on me? Yes, exactly. Because it's Newton's third law. It's an action-reaction pair. The magnitude of that force is G m1 m2 over R squared, right? So it depends on both masses. They're exerting the force on each other, and so it's equal and opposite. All right, very good. So now let's go back to our positive charge that we've called A. But this time, I'm going to take away the other positive charge. And the point where that charge used to be, I'm going to call point P. My question for you is anything happening at point P right now? Is there a force at point P, for example? How much force, if so? Yeah, what would we need to determine how much the force is? We would need K Q1 Q2 over R squared, right? Anything missing? Q2, right? Q2 is 0. Because there's how many charges? 1. So is there an electric force going on here? No. There's no force at point P. Well, that's what I'm getting at. Is there anything at P? Let's go grab that positive charge that we had a second ago and bring it and plop it down at P. Does something happen to it? Yeah, if I drop that positive charge back at point P, now we have a repulsive force, right? Now I take that and put it away. Let me go get an electron. I plop it down at point P. There'll be an attractive force. So there's something going on at point P, even though there's no force right now because there's not a secondary charge. There's something at point P. And we describe that as an electric field. Point A, or excuse me, charge A is creating an electric field at point P, to where if I drop another charged particle at point P, it's going to experience a force due to A.
What's the definition of that force?
We're going to derive it next year. For now, just know that it's a potential force at that point. And we're going to define that electric field. Not define as in the nature of it, but how to describe it. Maybe describe's a better word. We're going to describe the electric field as it's described by the potential force on a positive charge. Now, could we have just as easily described it as the potential force on a negative charge? Sure. It's just a convention. We're going to say it's... Alright, so at point P... Oh, and by the way, the symbol for electric field is capital E. So the field at point P is directed in which direction? Well, if it's described by the potential force on a positive charge, if I plop a positive charge down at point P, it's going to be pushed away to the right. So the field at point P is directed to the right. And so I can draw that, and field is a vector just like force. And so I can draw an arrow indicating the direction of that vector, and it is to the right. And actually, I'm going to shorten the arrow a little bit, and you'll see why in a second. Alright, let's pick a different point. M. What do you know about the field at point M? It's greater? Why is it greater? Good, because it's closer, and so if I plop a positive test charge down there, it's going to experience a force in which direction? Still out to the right, but it's going to be a greater magnitude because it's closer to the charge, right? And so if I draw the electric field vector here, it's in the same direction, but it's much larger than it was at P. Okay? Now what about at this point, Q? Is there a field at point Q? Yes, and it is directed down. Similarly, there's a point R. And the field at R is up. And I ran out of room. It should be one. Alright? So far, so good? Alright, well then let's, instead of a positive charge, let's plop a negative charge down now. And again, we'll pick our arbitrary point P over here. Yeah, there's a negative charge. So if I plop a positive test charge down at point P, it's going to experience a force in, towards the left. So the field at point P, due to that charge, is directed inward. And again, M has a field that is still in but greater. Q, now the field is up. And our R guy, the field is down. And by the way, those should have been, obviously these two should be long. They're equidistant of M, so they should have been as long as M. I got sloppy. Alright? That's pretty straightforward, right? No problems there. Now we're going to complicate things just a little bit. We're going to have a positive charge, but then we're also going to have a negative charge as well. I'm going to start with the point M between them. It's the midpoint, that's why I said M, right? So, what did we just say? What kind of quantities are fields? They're vectors. So, I've got to worry about their direction, and I'm going to have to add them as vectors. So, is the positive charge creating creating a field at point M? Yes. What's the direction of it? To the right. Yeah, because we're talking about the field due to the positive charge would be directed to the right, right? Oh, I'm sorry, the test charge. Yeah, by our definition, our description, the electric field is the direction that a positive charge would go. That's our convention.
Oh, so you can't do negative test charges?
Right, we never worry about a negative test charge. Now, I can predict which way a negative charge will go if I place it at that point based on the field. But the test charge is always positive. Right? But then what about this negative? Is it creating a field at point M? Yes. In which direction? The same direction, also to the right. So I'm going to add it as a vector to the other one. And the net field then, just like we did net forces, the net field is the sum of those two, the vector sum. So the net field is to the right, double what it would have been if there had just been one of the two charges. Yes, we're assuming the charges are stationary, and we're also assuming they have the same magnitude of charge, even though they're opposite in sign. Right? So that was pretty easy, right? Let's pick a different point and see what happens. Let's come down here. Call this point P. I'm going to move the label for P on the other side. I know. Yeah. And what's the field due to the positive charge? In which direction? Down and right, because it's away from the positive charge. And the field due to the negative charge is up and right, because it's towards the negative charge. And if P is aligned with M so that it's equidistant from the 2 points, then the magnitudes of those two fields are equal. They're just in different directions. So the net field, when I add those two vectors, is going to be straight right. Because the up part of the negative charges field and the down part of the positive charges field cancel. And so it's just their right parts that add together. You need that. I'm sorry?
So when you're drawing it, you don't add it to each other's magnitude.
Right. Well, I Right. What I'm going to do is I'm going to add them as vectors, and so I'm going to take this guy, and I'm going to put him, slide him down here, so that it's tail to tip. And so, yeah, so I actually should have made that arrowhead go a little bit farther. Like that. What's that? What do you mean, either way? Yeah. Right? What about this? What about this point Q?
It's the same thing.
Same thing? Positive is going up that way. Negative's down this way. And when I add those two as vectors, I get straight right. What about a point here? What do you want to call this one? Point Q? R?
Let's do a J first. Just J.
What about R here? Okay, the field due to the positive charge is going to be greater. Why?
Radial distance.
Good, because it's closer. Yeah, the radial distance is smaller. And so I've got a larger E due to the positive charge and a smaller one due to the negative charge. And when I add those two vectors, the vector sum looks like that.
Does it always go right through the middle, like angular, like split it in half?
No, this is definitely not. This definitely doesn't bisect because the distance is longer. Yes, yeah, when they're equidistant. In these examples, for P and Q, it bisected. But R is not equidistant between the two charges, and so it doesn't bisect. So if you
dotted line the same as the line that you drew above? And just
yes,
okay.
yeah, if I'm going to add those vectors, remember I slide it down to where I have tail to tip, and so that's all I've drawn is that if I add this vector to that vector, then it looks like that. Tail to tip vector. Okay. And so you can see if I do a few more of these, that I'm going to get field lines that look like this.
Oh my goodness. Stop.
It's an eyeball.
That's an interesting error. It's two of them.
And look at the directions.
What's up? I see a face.
Like with goggles? Like a face? What?
I don't see it with goggles. I can see a face. I can see like the
I see a face.
Hey, if you see a Miller Earhart, go for it. That's awesome.
Austin sees it too. I'm not the
Wait, what's around?
Yes, that definitely confirms your sanity.
Hey, that's my joke.
All right. Now notice, what we've just drawn is what we call an electric field map. It's showing the lines created by these, the fields created by these charges. And you need to know 4 conventions for drawing field maps, field lines. One of them we've already established, that these field lines are going to go from what to what? From positive to negative. The field lines are going to go from positive to negative. Because a positive test charge would do just that, right? It would run away from a positive thing and it would run toward a negative thing. So field lines are going to go from positive to negative. The second convention that you need to know is that the lines never cross. Right? Any Ghostbuster fans out there? Lines can't cross. Now, think about why the lines can't cross. What does the line represent? the path
I got my boy on something.
of what? Well, the electric force, right? On a positive test charge. If, let's say the lines crossed for a second. Let's pretend it did this.
No. 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 Bermuda Triangle.
If I'm at that point C, where those lines cross, the lines are supposed to tell me, by definition, the path of a positive charge. Well, if I'm at point C, how many different options do I have to follow? 2. Can that be true? Can there be 2 different directions for the net force on a positive charge at that point? No. So since there can never be 2 possible net forces on the same object in the same point, the lines of an electric field never cross. The third convention is that the density of the lines indicates the magnitude of the field. In other words, the tighter together the lines are, the stronger the field is at that location. And if I just draw an arbitrary square-shaped looking thing like this, a rectangle looking shape like that, compared to the same size rectangle here, right, at position 1 and position 2, what can you say about the density of the field lines in position 1 compared to the density of the field lines in position 2? They're closer together, right? The density of the field lines in box 1 is greater than the density of the field lines in box 2. So what can we say about the magnitude of the field at box 1 compared to the magnitude of the field at box 2? Good. It's greater at 1. And do I expect that? Yes, because I got very close to one of the charges, and when that radial distance gets really small, what happens to the force?
Oh, I know. It goes up.
It gets really big, right? It increases. Good. All right.